In this video, we're going to look at how columns of air that are closed on one end and open on the other create standing wave patterns. And some examples of instruments that would fit this pattern is stuff like an oboe, a clarinet, trumpet, trombone, saxophone, and even our voices, because they're going to be sealed off on one end, air is going to be pushed through the tube of some sort, and then be open to leaving. The sound waves will travel out the open end of the pipe. And so what we're going to look at are the requirements for building these standing waves. Now, if you look here, inside the pipe, when you hear a note, when the frequency is just right to create that standing wave pattern, you're going to find a node at the closed end, and you're going to find an antinode at the open end. This is always going to happen. So when you have that closed end, it's always going to form a node, an area of perfect destructive interference. And on the right hand side, it's always going to form that antinode when it's open when you hear a note. If the frequency is not quite right, then that antinode won't match up with the end of the tube and you won't hear anything. Since our wave is going from a node to an antinode, this is 1/4 of a wave. We're going from a point of equilibrium to a maximum, and so that would be 1/4 of a wave. That means that the first sound that we hear will happen when the length of the tube is exactly 1/4 of a full wave. And so to get the full wavelength inside this tube, we would need it to be 4 times longer than what it actually is. Now this first note that we hear, we call it our fundamental frequency, or our first harmonic. Harmonics are multiples of this fundamental frequency, that lowest frequency that will create a standing wave pattern inside the tube. Overtones are a term that we use to refer to harmonics that are above the fundamental frequency. So our first harmonic is the fundamental frequency. Our second harmonic is what we're going to call our first overtone, and third harmonic would be the second overtone. And so you can think of it over, above, tone, the note. So it's that next octave up. So for music people, that's that next cycle up, where you would play 2 notes and they sound the same, but one's exactly twice as high a frequency as the other. So again, harmonics and overtones are things we're going to be talking about in these videos. Now, in a closed pipe on one end, you'd have the node. Now, if we were to increase this wave to get half a wave, then there would be a node at the end of the tube, and a node is a spot of complete destructive interference, and so that would mean there's no amplitude, which would mean there's no sound. And so at the second harmonic position in an open closed pipe, you won't hear anything. So no sound would be generated. And again, the length of this would be 1/2 lambda if it were to make a sound. Now, the next note we'll hear will happen at what we call the third harmonic position. And that's because, again, we've got an antinode happening at the open end of the tube, which will produce a sound. And that's going to be 3/4 of a wave, because we go all the way up to a maximum, back to equilibrium, all the way down to a minimum, and that it would be 3/4 of a total wave. And so the pattern that we can then deduce from seeing this is that open closed pipes only produce sounds at odd harmonics, meaning when we have 1/4 of a wave, 3/4 of a wave. And so that's where we're going to get our equation for relating the length of the tube, L, the length of our column of air, N for our harmonic number, and lambda for our wavelength. Those are our 3 variables that go into determining how long a tube you would need to produce a certain wavelength that would then lead to a certain frequency note to produce the music or the sound that you want. Now looking back here, you might say, wait a second, I see the 1, I see the 3, but there's a 1/2 in here. Remember, 1/2 will be the same thing as 2 over 4. It's just simplified. So if we have 1 over 4, 2 over 4, 3 over 4, as we increase those harmonics, and only the odd numbered fractions are going to produce sound. Now if we rearrange that length is equal to 1/4 of a wave for that fundamental frequency, we would find that you'd need 4 times the length of the tube to equal a full wave. Now, our wave speed equation that we learned and talked about last week is velocity equals frequency times wavelength. So if I want to go based on the size of the tube to determine how fast the air is traveling or what note it's going to produce based on how big or small that tube is, I can actually substitute and use my system of equations, and I'll come up with the velocity of the wave is equal to 4 times the length of the tube at which the sound is produced times the frequency, the note that is produced. And so this is going to be our wave speed equation for the fundamental frequency of a open closed pipe. Now, if we move on to the third harmonic, the next one that produces a sound, remember that's the second overtone. Remember this one has 3/4 of a wave inside. And so if I rearrange that to solve for wavelength, I'm going to multiply both sides by 4/3 to get rid of that fraction that is attached to the wavelength. My 3's cancel, my 4's cancel, and I'm left with the wavelength would be 4/3 the length of the tube that you see here. Same as before, I'm going to take my velocity of a wave equation. I'm going to substitute for lambda, and the result is the velocity is going to equal 4/3 times the length of the tube times the frequency. We're going to look at one more, and I think you'll start to see the pattern here. So for the fifth harmonic, again, all I've done here is we're on our fifth harmonic, so this 5 is here. I simplified, solved for wavelength, and I got 4/5 the length of the tube equals the wavelength. Substitute, and now I've got 4 over 5 equals the length of the tube times the frequency of that note that's produced. To creating a generic equation for the velocity of a wave in an open closed pipe where one end is open, one end is closed, where the wave speed is going to equal 4 divided by the harmonic number times the length of the tube times the frequency of the note. And again, we can see that pattern here. This was the fifth harmonic, and that's why there's a 5 right here. This was the third harmonic, and that's why there's a 3 there. And while our first harmonic doesn't have a fraction, remember anything divided by 1 is itself. So this even follows the pattern. It's going to be helpful for this week's activity because you're going to be dealing with a tuning fork being hit over a PVC pipe, a tube, that is submerged in water. So the water would act as a closed boundary. The part that's open where the tuning fork is hovering would be an open end. And so you will be able to use the length of the tube, the frequency to determine the speed of sound, or you could even work backwards if you're trying to figure out how long the tube would need to be to produce a certain note, and that's what they use when they make instruments to a certain specification, and that's why certain notes require certain lengths of the tube, which is why there's keys on those instruments. It's also why when musicians tune their instrument, they're going to adjust the length so that these standing waves form and you get the notes that you want to hear.